So yeah, hi everyone. Yeah, welcome to another session of our review of the database internals book. So just to recap, last week we looked at leader election and yeah, that was basically looking at some algorithms that help decide what nodes in a distributed system you know get selected as the leader or the primary node. So this week we'll be looking at replication and consistency. My name is Damilola Ajiboye. Um, yeah, so why do we need replication, or what is replication? Uh, so we've been looking at distributed systems, and the common theme we've seen is we have systems with multiple instances or multiple nodes, and so one of the reasons we have that is because we want these systems to be fault tolerant. That pretty much means if any component in the system fails, um, we want the system to still work, as expected, or work correctly, even in the presence of failures. So to build fault tolerant systems, we need redundancy. And that's pretty much, for every component, every critical component, you need at least like a duplicate of it or as many copies of it, so that in case of failures, that the copy can, you know, continue the processing. So I think the simple examples you can think of is in an airplane. If you build a fault tolerant airplane, if one engine goes down, there's a backup engine that picks up, and the airplane does not crash. Yeah, another thing we want is availability. That's from the business perspective. You want the system to which is, if you look at it, they look similar. Availability, you also want the system to continue operating even in the presence of failures. But I'll say the difference is it depends. I think I looked into this, and what I found is the difference is when you think about it from downtime, right? So in fault tolerant systems, you kind of desire zero downtime. So like I said, in an aircraft, for example, you don't want any downtime because you don't want the plane to crash. Or let's say in a RAID setup of a DIX, you want to make sure that they are even if one DIX you crash, the system keeps working fine. But with availability, we can tune that and say, oh, we want 99% availability. So we're kind of going for 100%, but we can accommodate some form. So if you have a web server, for example, you can accommodate it being down for maybe 2 seconds, for example, and when it's trying to replace the dead node with another node. So if you have questions, you can just stop me, and then I would stop talking. Yeah, so these are the reasons we need redundancy. And when we talk about redundancy, and we've talked about it being having multiple instances of critical components, then we look at it in terms of the data, right, which is where replication also comes in. You want to have in these redundant systems, you want to have data copies of the same data across these redundant components. So that's where replication comes in. So whenever there are changes in this data, you want those changes to be synchronized across the redundant components. Yeah. So data replication is a way to introduce redundancy by maintaining copies of data in the system. So one thing the book talked about was geo-replication, which is when you think about having replicas across multiple data centers. Aside from the benefits of like fault tolerance, you also gain some benefit in terms of latency, which is kind of what we do with CDNs. So if the data is closer to the user in terms of like physically, right? So if I'm in Lagos and the data center is in Lagos, obviously the latency will be a lot better than a data center in San Francisco. Yeah, so that's another benefit we get when we look at it from the perspective of replication. Okay, so let's look at the cap. So that's very much consistency available. I should have there should be a comma there. Consistency, availability, and partition tolerance. So this is like, I think it's a theory, and the idea is in distributed systems, we have to make trade-offs between these three properties. So it's kind of not possible to get 100% of all this. You have to think about making trade-offs. So it's either you're making the trade-off in terms of availability or inconsistency. So let's just go through what they are. So like we said, availability, it's the measure of the availability, the ability of the system to serve a response for every request. So imagine we build an API. We want to make sure that every time a client makes a request to the API, we get a response. So that's pretty much availability. Keeping all servers operational to process transactions might lead to inconsistency. Yeah, so this is where you think about the trade-offs, but let's just go through them, then we'll look at the trade-offs. So we look at consistency. So I know we've talked about consistency in terms of the acid property, but where the difference between the consistency in acid and in CAP is in terms of acid is looking at it from the perspective of transactions, right? So consistency there is saying when a transaction starts and when we say the transaction is complete, the data invariants, things like unique constraints we said, or foreign key constraints and things like that should be preserved, right? So if a transaction is successful and we committed it successfully, if the unique constraints should be preserved, and you should not leave the data in an inconsistent state. So that's where consistency comes in ACID. But in CAP, we're looking at it from, having redundancy and replicas. And we're looking at it in terms of linearizable consistency, which we will still look into later. Yeah. Then partition tolerance. So we're talking about nodes in a distributed network. And I think earlier in the book, we've talked about network partitions, which is pretty much this occurrence that happens where nodes in the network cannot communicate with themselves. This could be for several reasons, like their physical network issues or maybe software issues. But yeah, we can expect this to happen. So part of the things we're looking at in CAP is partition tolerance. So whenever this partition happens, like how does the system handle them? So yeah, so let's look at the trade-offs. So CAP is pretty much saying that we cannot guarantee a system that simultaneously guarantees both availability and consistency in the presence of network partitions. So whenever we have these partitions, network partitions, we cannot guarantee availability and at the same time guarantee consistency. So that's where we need to make these trade-offs. So this just give some examples of some variation of these that we can have. So one is CP. So CP is if you look at the diagram on the right, you see the set that we have. So CP is pretty much you want to guarantee consistency in the presence of network partitions, but you guarantee best effort availability. So best effort meaning if there are no network partitions, you kind of you should have like availability, but you can't guarantee it when there are network partitions. So that's what CP is. So it guarantees consistency, but best effort availability during network partitions. So in these CP systems, we prefer requests to fail rather than serving potentially inconsistent data. So that's the trade-off we are making. So for example, in a banking system, you might want to halt transactions, during the network partition, just to ensure that all account balances remain consistent, because you don't want to serve like say, a wrong account balance in the system. Yeah, and then AP is the other way around, where we are guaranteing where we kind of prioritize availability over consistency when we have network partition. So in this case, we are cool with serving inconsistent data because our priority is availability. So we want these nodes to be able to yeah, respond to any request from clients. So an example here is the social media platform. So want users to to be allowed to update their post even if there's a network partition. So what that means is different users, or even to view posts. So what that means is different users might see slightly different versions of the feed of their feed, um, but this is fine because it's just Twitter, for example. Yeah. So why not CA, which is like, oh, why are we only looking at CP and CA and AP? That's because network partition is not something we can trade for anything, because it's not within it's not physically, it's not within anyone's control. You can't build a system where you are 100% sure that there will be no network partitions. That's because these things are built on like physical infrastructure. A data center can a bomb can be detonated in a data center, and then it goes off the network. No one can really control that, or a rat goes somewhere and bites some cables, and then we have network partitions. So we just have to design these systems thinking that network partitions will always happen. So another kind of trade-off the thoughts that came up is PACELC. So it's an extension of CAP, and what it's saying is that when there are network partitions, then CAP covers that scenario. So if you look at the diagram on the right, you see when there are network partitions, the trade-off is between consistency and availability. But when we look at on the left, it's between consistency and availability. But when we look at the right, this is saying that even when there are no trade-offs, even when there are no partitions, network partitions, there's this trade-off we have to make between latency and consistency. So that's what this is talking about. So CAP focuses on trade-off between consistency and availability during network partitions, and then this states that when there are no network partitions, we still have to make this trade-off between latency and consistency. So if you think about it, what that means is that if you have, let's just give some example. If you have a network with 1,000 nodes and you want like some form of strong consistency where once there's an update, every node should get that update, then you have to balance the trade-off between the latency. So if you have to make sure that every node gets the latest updates when you perform a write operation, that might take some time because these are network calls. So you need to make that trade-off. So we'll look at things like Quorum later, which shows how we can make those trade-offs. Yeah. So another thing to think of is, we talk about availability and high availability. So there's a difference between these two terms. So we've looked at availability in CAP, so I wouldn't go through that again, but I think what we focus on is CAP. Availability in CAP kind of doesn't have like an upper bound. So if you're thinking about it, it just says, like whenever there's a request, the system should always be able to respond to that request, but there's no time bound on how long that should, that request, the latency should be. So high availability is not just about the system being operational, but we want low latency as well. Yeah. Then consistency in this ACID and CAP, I think we've gone through that. So we would look at, so consistency in CAP is about making sure that the data, the replicas are uniform and synchronized. while in ACID is about keeping the invariants and constraints. So now let's look at yield and harvest and yield. So in CAP, what we discussed is the trade-off between consistency and availability, and those are kind of like, that's like the strongest form of the guarantees, right? So consistency is saying that all the data across all the nodes should be synchronized. And then availability is saying we should always be able to respond to requests. Like if you make 1,000 requests to a service, we should be able to get a response each of those 1,000 times. But in yield, we are kind of relaxing that and looking at it from a weaker, like looking at the weaker form of these two terms. So harvest is saying it's asking the question of, can we look at it this way, like how much useful data can we get from the system, even when parts of the system are down. So in the example here, you have a search engine, and there are 100 results for the search query, but the search engine is only able to fetch 80 because there's some parts of the system are down. So if you look at it, is it fine to just return 80 search results, because most users will probably not scroll past like the 50th result. So it might be fine. So harvest in this case might be a way to look at making these trade-offs. Then yield is looking at the proportion of successful. So this is like the weaker form of availability. So it's saying if we make 1,000 requests, per minute to a web service, and we get only 950 requests, is that fine? So these are just two weaker forms of consistency and availability. So let's look at shared memory. There's something the book has talked about. So we'll just go straight to register. So the book talked about registers as a single unit of storage that is accessible for read and write operations. We have registers in like, I think they're in processors, right? So if you have like it's by, ARM processors, they have registers in those processors, and I think it's 8664 processors. So, but we're looking at this more from like I wouldn't say logical, but when we are thinking about consistency and what exactly are these read and write operations performed against, we're looking at them in terms of like a register. So we can view shared memory in a distributed system as an array of registers. So another thing to think about is sequential and concurrent operations. So we have read and write operations, but how do we know when they are sequential, when they are concurrent? So we can look at operations as having two events, an invocation event and a completion event. So in the diagram here, you see that let's say for a read operation, there's an invocation and there's a completion. So the first diagram on the left shows like what is sequential flow looks like. So the first operation has to be done before the second operation, and then the second diagram shows what concurrent scenario looks like, or overlapping scenario where we have operations that are overlapping. So the book also talks about types of these registers. So we'll just run through them. So we have safe, we have regular, and we have atomic. And the difference is pretty much how it's mainly in how these registers, handle concurrent operations, especially concurrent read-write operations. So let's look at overlapping read-write operations. So let's look at safe. So if a read operation that is not concurrent with any write operation, the expectation is it would return the value written by the latest write operation. So whatever the current value is what the that read operation will return. But in the case where you have concurrent operations, read and write operations, The value is could be any value, but should be within the range of the allowed range of the register. So I know we discussed this on the channel, and pretty much what we've seen is, it means the range of values that are allowed to be stored in a register. The simple example is if you have a register that is a binary register, meaning you can only store two values, 0 and 1. In this scenario for safe registers, and when you have overlapping read and writes, if you have the response can be either 0 or 1. It's not, you can't determine it. It could be any of that. So you have this flickering effect where if you have multiple reads and and there's a concurrent write going on, you can get 0, 1, any of those values. Then you look at regular. So regular it has a stronger guarantee than safe registers, and there are two values it could return. Yeah, similar to save, it will return the most recent completed write operation. But if there's a concurrent write going on, it could also return, the value that is written by that concurrent write. So that's where regular is different. And then the strongest form is atomic. So every write has we'll look at linearization points later, but this is kind of stating something similar. So it's every write has a well-defined point, where from that point any read from that point would return whatever value that write has written. So unlike regular, where if there's a concurrent write, we can either see the most recent completed write operation of the concurrent one. In atomic, let's just say you don't really observe the side effect of the concurrent write until it crosses a particular point. So it's any read before that point would always return the recent completed write, and any read after that point would always return the value by the write operation. So it's a simple example here. So you have a back account read, let's just say R1, and when there was an ongoing write of W2, so R1 will return B1, right? Because this write is still ongoing. But once this R2 has crossed that point, once W2 has crossed that point, then, every read would return B2. So this will make more sense when we look at linearization point. Yeah, so look at ordering in distributed systems. So this is just stating that, defining the order of operations in a distributed system is very difficult, and it's similar to the what you see when you work, when you're looking at concurrent programs that have multiple threads and race conditions and things like that. You can define like the order in which the instructions of those different threads would be arranged, because it's up to the processor to decide that. So so it's similar challenge you have in distributed systems, because now you have multiple nodes and multiple clients all processes trying to perform read or write operations. So that's pretty much what this slide is. I don't think we need to go into much details. Yeah, so on the right was just an example of the different possible scenarios. Yeah, so we'll look at consistency model, which is I think the chunk of this page. Consistency models. So why do we have consistency models? So we've discussed why order in ordering in distributed systems is difficult. But if we just allow things to work this way, like, it would be difficult for us to design or make predictions about how our distributed systems are meant to behave, right? Pretty much will be hard to predict the outcome of when multiple processes are performing read and write operations. So consistency models kind of help us define this orders. and outcomes. So so to reason about operation order, we need to provide clear descriptions of possible outcomes, and that's where we need consistency models. So they help manage and predict the behavior of read and write operations in distributed systems. Specifies the rules and expectation for the order and visibility of operations when multiple clients are performing this operation simultaneously. So that's pretty much what consistency models are about. It's how do we define, the order and the visibility of operations, redirect operations, when we have multiple clients performing this operation simultaneously. So there are two perspectives you can look at consistency. One is state and one is operation. So state is focusing on the correctness of the data and the relationships of the data that are across the replicas. So it's kind of like the end state, right? And then operation is looking at the order and the execution of the operations themselves. So we have the operations like the read and write, and we have like the final states that those operations lead to. So there are two. So you would see consistency models that look at these things from this perspective. Some look at it from the state, and some look at the operations. Yeah, so let's look at one. The first one is strict consistency. So as the name implies, it's like the most extreme one. So what it means is that, so it implies that any write by any process should be instantly available for subsequent reads by other processes. So what that means is that, if we have multiple processes trying to, perform this operation. So if a process should perform it right, we want it to just synchronize at the same time, like instantly, to all the other processes, which is why this is the most extreme. So it involves the concept of a global clock. So we'll just look at this. So any read at time 2, after a write at time 1, will return the newly written value. So this is one expectation that we have in this particular consistency model. So the challenge with this is it's impossible to implement this in like real world database systems. And this is because this is like expecting that immediately you make a change, right, to the data, that at that instant time. So let's say this time 1, at time 1, all the nodes should get that update and should be updated, which is not possible because we have this networking speeds are not at the speed of light, for example. Even if it's fiber optics, and there's still some nanoseconds or something that will be involved. So yeah, there would always be like some delay in real systems. So network latency, our protocols are not perfect. So TCP, for example, has error corrections and retransmissions, or the packets can get lost and then it has to retransmit. So these are all the issues they have on the physical layer that makes this particular model impossible. You can't have instant updates or synchronization across all the nodes in the network. So that's why strict consistency, it's said to be impossible. Yeah, so we look at linearizability. Yeah, so it's the strongest single object, single operation consistency model. Single object in the sense that most of these consistency models we are looking at, we're looking at it from the perspective of multiple processes carrying out redirect operations on a single object, right? So single object can just be like on a particular data or variable or something. And then single operation means we're only looking at it from just single operations. We're not looking at the consistency across like a complex set of operations. Yeah, so it ensures that operations appear atomic and they are ordered consistently across nodes in a distributed system. So when it says it appears atomic, is in the sense that if an operation, is atomic, that means it's either done or not done, right? So there's nothing like partial completion, right? It's indivisible, and that's what we are trying to achieve in reusability, right? Operations should just appear atomic or appear like they happen instantly at a particular point in time. Yeah, so that is where we have linearization points coming. So if you look at the diagram at the bottom, so like in this consistency model, it's not, we know that it's not realistic for operations to just be instant. That means if you, I mean, if you take it to like the instruction level, right, there are probably instructions that are like one clock cycle, which sounds like instant. But I mean, those are not the instructions we are working with in a distributed system. So we know these are things that are going to run for like some maybe microseconds or something, but we still want them to appear atomic or instantaneous. So how this is achieved is you have the invocation point and the completion point, and then you have this point called the linearization point, which is here between the invocation point and the completion point. So what this means is that whatever effect that operation is meant to have doesn't become visible to other processes until we cross the linearization point. So that's how it would appear atomic, because to other processes, it's just going to appear as if that operation and the side effect of the operation happened at an instant in time, at a particular time, even though it took some seconds for the operation to complete, but we only see the result when we cross the linearization point. Yeah, so that's what linearization point is. So another criteria in this consistency model is sequential process local order and global real-time ordering. So what sequential process? Oh, I should have added some diagrams that would affect. Let me see if I have any. Oh no. Okay, so sequential process local order. It's so we're looking at different processes, right, carrying out read-write operations. We want to make sure that in this consistency model, it's making sure that the order of the operations carried out on a particular process is preserved. So look at yeah, it says if a process has an operation A and then an operation B, it has to maintain that order, right? So A must come before B, right? So that is when you look at it from the perspective of a process. But global real-time ordering is now taking it to, like, I'll call it inter-process operation. So it's like across operations, across all processes. We want to make sure that if a process in process one occurred or happened before a process an operation in process two, we want to make sure that order is preserved. So global ordering should also be preserved. So these are two forms of order that needs to be preserved in linearizability. Yeah, I think we can. So comparison with strict consistency here, because that was confusing to me as well. Like, how are they different? So, so the major difference, like we said, in strict consistency, it expects this propagation or synchronization across all nodes to be instant, right? But in linearizability, it allows for, like, it's practical. It's like here we can have like delays in the propagation, but the main thing in linearizability is making sure of is that before we say an operation is successful, at the linearization point, the side effects of that operation has to be visible to all the nodes, and then then we can see the operation is successful. Yeah, so the cost of linearizability, it's mainly in the the synchronization that is required, especially when we talk about the linearization point. So that means for every operation, you need to make sure that for you to pass the linearization points, this requirement that all nodes should the side effects of that operation should be visible, should be, needs to be ensured. And then the ordering as well also incurs some cost, because now nodes have to come up with like some form of consensus to agree on the order of operations, both in terms of like sequential process order, and then the global order as well. Yeah, so let's look at RIFL. I think, yeah, this is one implementation of a linearizable remote procedure call. I won't go into much details, but this is one example of an implementation. I've shared like links to some blogs that I read that were really helpful. And you know what, it's trying to ensure some of these constraints that we've seen in this consistency model, and it does it by using things like a lease, a client ID, and yeah, and that's how it's able to track the order, and also make sure that we have this linearization point possible. Yeah, so let's go to sequential consistency. So this is another consistency model. So this is a relaxation of linearizability, because we've seen that can be very expensive to achieve. And so what sequential consistency does is it's less stringent in just one part of the requirement, which is in the requirement for real-time global ordering, right? So it still holds the requirement for like process local ordering, right? So every the order of operations carried out in a particular process has to be maintained, even in the global ordering. But in terms of like operations across ordering across operations, or across all the processes, it doesn't require real-time ordering. So it's fine in this consistency model for you to have an operation that started in process 2 that started before an operation in process 1 still appear the other way around in the network. So that's the difference between sequential and linearizability. Yeah, so the screenshot on the right is just showing what this looks like, and if you see it, you can see that the read, the way the changes are observed in clients 3 and clients 4. Another important point is, even though it doesn't require real-time global ordering, it still requires that the order is consistent across all the observers in the network, right? So if, for example, in this example on the right, we can see that client 3 and client 4 observed change 4 before change 3, even though when you look at the real-time ordering, 3 happened before 4. But the main thing is that both clients are consistent about their perspective of the order. And so that relaxes the requirement a little bit. So let's look at causal consistency. So causal consistency, in causal consistency, what we're looking at is more about like cause and effect, right? It's the order we're looking at is for every operation, we want to make sure that it's the order is based on some relationship that it has with the previous operation. So I think a simple example would just be like, yeah, I think in the book it talked about like a chat thread. I used like an email thread, but threads basically. So where there's a message, maybe hello or something, and then there's a reply, right? So in the network, we need to see the messages in that order, right? So even if the messages are propagated at different speed to the network. So for example, if let's say the order is hello, then hi, I mean hello, and then the reply is how are you, and like how are you doing? Even if the second message gets propagated faster in the network than the first message, all the nodes need to, be able to determine like the relationship, the causal relationship between these two messages, and make sure that they are ordered in, correctly. So this is not about like time ordering, it's about a causal relationship. So that's what this consistency model is focused on. So there's no global, you don't need a global order. It's just all about causal relationships. So here, one of the things that is very important is a logical clock, which is not, it doesn't really deal with like time. It's more, I think most of the yeah, most of the things I read about it, that's to do with, is mostly uses like some form of sequence numbering, right, or order. So that, just imagine every message or every operation in the network has some form of sequence number, right? And so that allows nodes to know the relationship between messages. So if a message with a sequence number 2 comes before 1, it knows it just needs to buffer that message and wait until it gets message 1. Kind of how TCP packets work as well. I mean, there's some form of yeah. If we look at how TCP packets work, that's how it's able to packets can get sent and arrive at different times, and then the network card or something can rearrange those packets so that the data, the bytes are correct. So that's kind of what's happening in causal consistency. Another type of clock that is used is vector clocks. And then these are some real life implementations. Yeah, so session consistency, this is looking at it from like the client's perspective. So it's called a client-centric consistency model. Some of the properties of this consistency model is let's just go through them. So one is read on write. So this is very important. So this just says that for a client interacting with the network, right? If the client issues a write, immediately the client and then immediately the client issues a read, the client should, that read should return the write that client wrote, right? So that's what that, which is very important, because due to like the things we've talked about, how the updates propagate across the network, right? There are some consistency models where we'll look at eventual consistency. For example, you might have like some cases of stale reads there, but in session consistency, we are ensuring that from a client's perspective, if a client writes a particular value and makes a read immediately, it should see that value regardless of network partitions or anything going on the network. So monotonic reads, this means that if a client reads a value, it cannot read an older value. So once a client reads a value, whatever values were before that, it can't go back. It has to, it's kind of similar with what we saw in the linearization point, where once you cross the linearization point, every read has to read, values or changes after the linearization point, and cannot go back and read the change before the linearization point. So that's kind of what's happening here. But this is from the perspective of the client. And then we have monotonic writes. So writes from a single client must be observed in the order they were issued, which is similar to what we saw in sequential consistency, but this is from the perspective of clients now. So if a client, issued a particular write in a particular order, maybe 1, then 2, then 3, you should always observe, those changes in that order. And then we look at writes follow reads. So this is some form of causal ordering as well. And the idea behind this is, if a write, should have written an example that would help, but the idea behind this is, if a write is as a result of a read. So let's just put some numbers. So there was a read where we read 1, and then based on that value, we wrote 2. That's what write follow read means. So if a client reads a value and then writes another value, the write must be observed after the read. Yeah, so pipelined RAM as PRAM consistency or FIFO consistency. So it's like when you combine these three, okay, we looked at four, but if you combine three of them, monotonic writes, monotonic reads, read on writes, you get this consistency model called the pipeline RAM consistency model. And it guarantees the things we've talked about. Yeah, so let's see. I think there's a comparison with sequential consistency here. So if both do not require real-time global ordering, but in sequential consistency, the order of interprocess operations, that's when you look at all the processes and the operations across like global scene. Uh, when the observers, because I know we looked at that example here, so the criteria here is we don't really care about real-time global ordering, but we need to make sure that all observers observe the same order, the same global order. But in PRAM, we don't care about that. So observers can observe inter-process operations in different order. That's because we really care about it from the perspective of a client. So a client or a process should see the only order it cares about is the order of its own operations, not the order of other process operations. Yeah. So eventual consistency. So this is a relaxed consistency model, allows some divergence between nodes, and the guarantee here is that the updates will eventually propagate through the system over time. So what this and the updates need to be propagated. We just expect that this update to get propagated. So in case of a network partition, for example, whenever the network partition is resolved, we expect that these replicas would sync and get updated. So asynchronous update propagation, that's one of the properties of this consistency model. Conflict resolution. So in a case where some particular nodes have divergent values, because as a result of this eventual consistency, right? Like you would have cases where a particular node has like older data than, other nodes. So we need like conflict resolutions on how to resolve this whenever the partitions are gone. So one of them is last write wins. So that pretty much means the most recent, every write will have like some form of timestamp. And then the most recent write would be like, the write that all the nodes we agree on to make sure that everyone converges again. Vector clocks is another, it's coming up again. It's another way we can reconcile conflict in eventual consistent systems. Yeah, another thing we can see is there's no hard time bound. So we're saying eventually the system, all the nodes will get the latest updates and the system will be consistent, but there's no hard time bound on that, which might be an issue, and there's something to take note of. So now we'll look at still on eventual consistency. There are like three variables that are usually tunable in these systems. And we'll just look at them. So one of them is the replication factor. So the replication factor is the number of nodes that would store a copy of the data. So pretty much how many replicas do we want to have on the system? Write consistency. So this just means whenever there is a write, for the write to be acknowledged as successful, or marked as successful, how many nodes, how many replicas have to acknowledge that write? And then read consistency is, for a read to be, or a read operation to be successful, how many nodes have to, respond to that read request? So we'll look at how some of this tuning can be used. So we look at Quorum. Still related to what we just talked about, where we can tune some of these variables. So a quorum is the minimum number of nodes that must participate in, an operation for it to be um, marked successful. So in a system with n nodes, a quorum typically is at least, n over 2 plus 1. Pretty much majority of the nodes on the system or in the network makes a quorum. And so what are types of quorum? We have write quorum, we have read quorum. So write quorum is the number of nodes that must acknowledge a write operation, and then read quorum is the number of nodes that must respond to a read operation. So we look at some configurations here. So one important thing is to ensure consistency in the network, right? This is one, what the calculation should look like. So the write quorum plus the read quorum should be greater than the number of, nodes or replicas or the replication factor. So let's look at two examples. If you look at a write heavy configuration, what you are trying to optimize for when a system is write heavy is faster writes, right? So you can just in this case you can just say the write quorum should be 1. So that means only one node in the network has to acknowledge the write. So that makes write a lot faster. And then for reads will be slower, because if you set read to n, that means every node on the network has to acknowledge a read. So the benefit of that is that you would have very fast writes, but always consistent, because every the read can only be successful if after every node has been updated. So the opposite for read heavy configuration, just similar concept as well. Let's see if we have 2 minutes more. So witness replicas. So this is a way to reduce the storage cost in this system, in these systems that we've been discussing, where we have like replicas. That's because if you have like, I don't know, maybe 100 replicas, it's expensive to have every replica storing a copy of the data. So that's where witness replicas comes in. And what this means is you assign some replicas to be copy replicas, and then some will be witness replicas. So the witness replicas they just hold some metadata, right, to indicate that a write operation has occurred, but they don't hold the actual full data. I know they have something like this in one of those crypto networks, I think in Bitcoin, where you can have like light clients and I'll say heavy clients, maybe that's the wrong term. So light clients just hold like some metadata, and then the heavy clients hold the blockchain, which is like gigabytes of data. It's the reason why they have that as well. So it's similar concept here. But the good thing with this is whenever a copy replica is down, a write replica can be upgraded to act as a copy replica in the meantime, and then store full records. So that way we still have the quorum that we configured. And then whenever the copy replica is back up, it just needs to sync. And then once it's up to date, then the write replica, goes back to just being the witness replica goes back to just being a witness replica. So this is an awesome way of reducing storage cost. And I think we are on time. So strong eventual consistency, it's a middle ground between strong consistencies like linearizability, which is the very one of the the strongest one, the strongest practical consistency model, and then weak consistency models like eventual consistency. So what this does is the updates are still eventual, like they can propagate late or out of order, but whenever they reach all the nodes, then whatever conflict has occurred can be resolved, so that the system can be consistent. And one of the ways this is done is with RDTs, which is a conflict-free replicated data type. And since we're out of time, I think the idea behind this is that the operations don't change the state of the data. They are just more like they are just operations without side effects, right? It's more like you're just storing those operations, and then whenever there needs to be a merge, having to synchronize with other nodes. That's because these operations don't have side effects yet. And then whenever the network partition is resolved and we need to synchronize all the nodes, all that has to be done is a merge. So where every node propagates whatever operations they have locally, and then once that is done, then you just have to merge all the operations, and yeah, and then all the nodes will arrive at the same states. So some example is the grow counter. So in this case, every replica maintains its own count. And then whenever there's a merge, all that has to be done is to merge all the the counts from all the nodes, and then every node would arrive at the same total count. Yeah, so that's it. That's the last slide. Yeah. All right, thanks. So any questions? Yeah.
I had like a bunch of like notes of like things to just maybe discuss towards the end. But like if anybody else has like questions, maybe they should ask, because they're fairly straightforward, like simple things to just kind of like talk about. Anybody want to go? I will take that as no. Okay, so the first, I guess, question is, initially in the first part of the book, we talked about transactions and concurrency and databases and things like that, and now we're talking about concurrency and distributed systems. So before we were talking about what is serializable and what is like linearizable. So what's kind of the difference there, and if any, like those two concepts, because they both deal with concurrency. So maybe if you could, just share your thoughts on that.
Oh yeah, that makes sense. I mean, from what I think is that when we're talking about serializable, we're looking at it from the perspective of we have this data, we have these pages, or let's say we're using B-trees or log, I think they're called LSTs, right? And then we have queries that converts to like a bunch of operations that we want to carry out on these particular pages, right? So what I think in that case is it's from the angle of, let's imagine we just had one instance of a database, right? A database is a server that can have multiple clients. So that's where the concurrency would come in, because multiple queries can be, going on at the same time, and then making them serializable is trying to, it's kind of similar to what we are trying to achieve in linearizability as well, right? It's trying to, make them appear sequential. So even though we have concurrent queries happening, how do we make them appear sequential? And then that's where we came up with all the different you know techniques that can be used to achieve serializability, and in cases where we might need to relax some of the requirements for serializability. So I think there are similar concepts but from different perspectives. So if we look at that from just operating on from looking at it from, we have a database server and then we have concurrent processes trying to run queries and make changes on the data, that makes sense. But I think this is looking more in terms of like replication, right? So replication is more like we have done those changes, the database server has carried out whatever changes it needs to do on the data, and then we need to replicate the final state of the data. So whatever the records are, we need to replicate it across multiple replicas to achieve high availability, so that in case if a primary node dies, we can pick up a replica and then we are we are still able to achieve high availability or availability. So that's kind of how I look at the difference. But good point. I think they are very similar concepts.
Yeah, sure. Sorry for even asking. It's kind of like one of those like brain teaser gotcha questions. Sorry. A better question is like, so like someone was mentioning like Raft. We haven't gotten to Raft, but like in the context of like we're talking about eventual consistency, right? And we're talking about quorums and how like you can tune the quorum to either serve reads or writes. Uh, if you didn't use like quorums, right? Like what if you would use like something else? Like is there like what's the reasoning or like why would you want like a quorum in the first place for eventual consistent databases?
Yeah. So I think the reason for quorums is like we saw in the what's it called? I don't know if there's a pronunciation for this thing. It's PA. Yes, so this thing, right? So it says like, oh yeah, even if we don't have network partitions, we still need to think about latency, right? So with eventual consistency, we know that the change is going to propagate to all the nodes in the network, even either whether there's a network partition or not, it's going to get there at some point, right? But we might want to optimize for the latency of reads or writes, right? So if we want our writes to be really fast, we know that we need to reduce the write quorum. So I think that's where the tuning comes in. I think is when you really think about this trade-off of latency versus consistency. So if you want to have very low latency, then you can just set the quorum to 1, the right quorum to run at, and that means only one node has to acknowledge, and you don't need to wait for multiple nodes to acknowledge. So that's one reason I think we have quorums. The other reason is the typical reason why we have redundancy in the first place. You want to, if you remember the formula that is here, let me see, yeah, this W plus R greater than N. You want to make sure that you have the right number of, write quorum and read quorum to ensure that you have this read or write consistency. So I think it helps to reason about this a lot better, depending on how much latency you are willing to sacrifice, to get like this consistency. I don't know if that makes sense.
Yeah, it totally does. So like yeah, like so we the Raft was brought up, right? Like, and I guess it's one of those like very popular I don't know, but like it does like involve like trade-offs, right? So if you were to just slap on Raft onto an eventually consistent system, you might end up with more latency. Like the data would be more consistent, but yeah. So yeah, that makes sense. I think those are mostly just my probing questions. Thanks.
Yeah, thanks. Yeah, any other questions? I tried spending some time looking at, I don't know if anyone looked into vector clocks. Yeah, I tried looking into it, but it was taking a long time for me to figure it out. So I would have loved to discuss, but if anyone, if there are no questions or if anyone looked into it, I would like to share what they know about vector clocks and how exactly do they help in resolving divergence in eventual consistent systems, or even like why do we even have divergence in eventual consistent systems. Yeah, that might be a good one to add if anyone looked into that. Yeah.
I would love to like jump on that, but I guess this is like a recording. Should we keep going? Do you guys want to keep going?
I think we're happy to. We might do some minor editing at the end of when we upload to YouTube. So yeah, feel free to just go on.
Okay. So like, so I think your intuition about like vector clocks and logical clocks is pretty like you're right there. So like you said, like you don't have so maybe a better, sorry for asking you like a question, but like I'm going to try to maybe like have a conversation. I don't know how much to assume you know already about like what is a logical or a vector clock and where like your point of confusion is, because like your intuition about that, it's a like a local counter that you kind of share in between systems, and then you have like a delta thing. That is correct. So for you, what do you think is like the most confusing?
Yeah, so it's how the counter and the vector clocks are updated, and how because one of the things I read is you'd be able to detect concurrent um, operations have been done between like two nodes, and then you can try to resolve whatever divergence or conflict that comes up as a result of those concurrent operations. So that's my confusion. Like the counters, so my understanding of vector clocks is every node has like a vector. Let's just call it like an array of integers, for example. So if there are three nodes, then every node has an array of size 3 or length 3,
Yes.
and they all initialize to 0. And whenever a node wants to carry out an operation, it increases its own counter. So let's say the index represents the index of every node. So it increases its own counter. Whenever a node propagates its vector clock to another node, the receiving node would compare the counter on that. Like let's say node A propagates its vector clock to node B. Node B would compare its whatever its counter is with nodes A's counter and do like a max, and then whatever the max is, it updates. I think that's where I got confused. Like, so how exactly are we going to be able to detect like concurrent? Because to detect concurrent
The,
operations, they have to have equal numbers or something like that, equal counters. Yeah.
So the funny thing is, like, you've literally described the exact like algorithm, right? So like you have like node A, node B, node C, and so let's say you're using like not let's say you're not using like a logical clock, right? You're using the like a normal like the wall clock. Like you're saying, okay, give me the current time from like the Unix time, whatever, right? Like, and you do that. Node A, node B, node C, all of them, once they initialize that clock at that exact same time, there's variance there because the clock is NTP and stuff like that. But like the basic idea is that if they at that exact instance, right, all those like times are going to be equivalent, right? So like because like like as humans, right, like we say it's 8 o'clock, but like if you have two different humans who have their own like globally all say, okay, this is the current time for all of us. So the only way to do that is that, you just have a counter. Like, so you have a counter on node A, you have a counter on node B, and you have a counter on node C, right? So when you compare those counters between each node, you're going to be able to vary that with like a delta. So there's a bit of a difference between like a logical clock and a vector clock. I think it's, where is it here? Yeah, so a logical clock can also use like the wall clock plus some stuff. So you can take the current timestamp, you can append like a random number, or you can append like a sequence number, and then you can compare those timestamps. And it can give you a causal dependence between what happened on node A and what happened on node B, right? Because the execution times can become mumbled up. Like there is no global sense of time, so everybody has their own view of time. So you need a way to resolve that. I don't know if I'm rambling. Does that help?
Yeah, I think I get the part where, yeah, like it's really hard for every node to have like the same time, no matter whatever time protocol they use, there would probably be some delay difference. I also get the part that so they maintain their own form of time, let's say using these counters. Yeah, I think it's just how we're able to detect conflicts, for example, or like concurrent operations have gone on between, across two nodes, and try to, resolve whatever conflict that arises around that. That's the part I couldn't figure yet. Yeah.
So technically, there's this thing called like a Lamport diagram that shows like a causal relationship between two events, right? So like this is one of like really hard thing about distributed systems, is that like you're never particularly sure about what is happening when, right? Because you don't know. So all that a logical clock gives you is you can be sure of the relative ordering between A and B, like node A and B, but that's all. And then node A and B can like do min-max or like whatever, right? And B and C can do min-max. So it's like a causal dependence. It's not like an actual time. It's just the time differential, if that makes sense, between like the observed states on both nodes.
Oh, okay. Yeah. So the logical clocks help with like defining that, identifying the causal relationship between like the operations that are happening across the nodes.
Yes, exactly. Like literally the algorithm that you described, right? Like before you take like you have like an array and then you're appending to it, and then eventually like you do min-max between two of them. That's basically it.
Oh, okay. Yeah. I think I'd also spend some time like looking into like maybe like an implementation or walkthrough. Maybe that would help also. Like, yeah, but I think I get like kind of like the algorithm. Yeah, but I just feel maybe like with a walkthrough, I'll get it completely. Like look at how it works in like different scenarios.
Yeah, fair enough. That's what I've been rambling about like on the Discord, right? Like there's this like bunch of like very small like challenges that you can kind of unit test and then write your own code against, and then do you implement? You don't necessarily implement like a vector clock, but you need to implement like a random like a UID generator. So and then you kind of run into this stuff, and then the code is not actually like complex. It's just I don't know. The concepts can be very, for me at least, like it's very sometimes can just feel very abstract. So yeah, I'm totally there with you.
Yeah. All right, thanks.
All right, so I also read a little bit on vector clocks, and I just wanted to like share my own understanding. Maybe that will also help you, understand.
Yeah, sure.
Yeah, so from what I understood and like what you already described, they're basically a vector clock is made up of logical clocks from each node. From what I read, the logical clock is in the node, and sort of a combination of the three of them showing each one's logical clock is what's is called the vector clock. And logical in the sense that it's not actually time, it could be another thing that is used to represent something as easy as counters. So from 0, the vector clock, all the values are initially set to 0, meaning all of them haven't processed anything. So, but when they receive a message or when a write is performed, each node has its own logical clock, and it could only modify its own logical clock. It wouldn't be able to modify, node A wouldn't be able to modify the logical clock of node B, which are all in the vector clock. So you might have something like 000 at the beginning, and if node A receives a message or processes something, it would increase its own logical clock to 1. So now it's at 001. And then maybe when node B receives a message, it increases its own 2 to 1. So now you have 110, but on node A, it still has 100, which is just for itself. And then on node B, it has 010, meaning it's only increased its own, it doesn't know what others have done. So when eventually, when they're able to communicate and share their clocks, then they will be able to combine that perspective and see, or you receive the message and confirm, I also have that message. So maybe node A received the message and processed the write request. So node B would be able to know that node A has done something and might also make sure it has a copy of that data or something like that. So that was my own sort of understanding or perspective on logical and vector clocks. I read a little article, quite short, on Gig for Gigs. Maybe I'll share the link later, but that was basically what I understood. Hope it helps.
Yeah, totally. Like you're also exactly right. Like, yeah. Oh, this was nice.
Awesome. Yeah, thanks again, Damilola, and thank you to everyone else for contributing, joining today. We'll just end it now and have a great rest of your weekend for the last few hours, and see you on Discord and everywhere else. Bye.
Right. Bye, everyone.